So hold on, help me understand this. So you're saying I'm not grasping the link between robotaxi and outsourcing inference, because if the go ahead.
Okay, so I understand where you're
excited.
Yeah. I'm stimulated here.
Yeah.
Okay, so currently, XAI trains one of these AI models like Grok.
Yeah.
They hand that off to a data center like Oracle, and then when you run a query, it goes to the Oracle data center.
Yeah.
What Elon wants to do with the robotaxi fleet is when it's not being used for FSD, all of those chips there and all those vehicles become a cloud data center.
Got it.
That all makes sense?
Just like
Got it.
a Powerwall, at your house can provide power back to the grid when you're not using it. These distributed chips that are capable of doing inference can then be connected together and do distributed inference for small jobs, as long as the job itself is not too big. Or if you don't have time, like it could be a big job, but if you don't care about how long it takes to do the job, then you can afford the latency that comes with doing it on lots of little computers that are spread out and have a lot of, networking latency built into them.
So it's like a good way of thinking of cybercab at scale as an example. So when they're doing 5 million units per year or whatever, 10 million, whatever the number is, these are all actually multi-purpose units, right? They provide transportation. They're also energy storage because they have a battery, and they're also distributed inference compute because when the car is not running, that compute is available. It will send a signal to the mothership that will say, hey, I think I have X number of seconds available for you to tap my chip to run an inference query. And then if it's not done, it will ship the package off to another car or to some server somewhere, and then they will finish the job. So it's kind of like, okay, got it.
Yep.
And it also solves the problem of power and electricity with data centers, because all these vehicles come with a battery built in. They can, So once you start looking at, go ahead.
And there's one more additional thing here. If you can buy more chips, obviously your cost per chip goes down, right? So you've got the ones that you're shipping out in the car, you've got the other ones that you're shipping out in the Optimus, you've got the ones that you need in the data center to do your training. But then what if you do like in between size that then you put next to every single mega pack at every single solar farm? And that when you have, like you can think of, there's a trade-off here where do you want to store your electricity as energy, or do you want to turn that energy into compute to do some useful work? And
which you get paid for.
Which you get paid for, exactly. And so if you are generating way too much electricity out in the middle of nowhere and you don't have a way to get that electricity efficiently to customers in the city, well, yeah, but you could do your inference there. And so then you could have kind of a intermediate, like a middle layer of, you've got the big things in the data centers to do training, you got the little things out at the edge doing useful work, and then you've got these middle things that's kind of interwoven into your energy layer, that those can also do training. They could do training, they could do inference, and that interconnection with your energy infrastructure, obviously, like this is the thing that people have been talking about with Bitcoin for so long, is like, why don't you have Bitcoin mining and, right next to your energy resources? And, this is something that a lot of people have done. If the energy resources have enough spare energy to where they can run your chips full out all the time, because like the competitive marketplace for doing Bitcoin mining is so intense that basically the only way you can stay right side up is if you can run your mining rigs full out, 24/7. And so that's hard to do if you can only use energy half the day. Well, you're obviously not going to put a Bitcoin mining rig as they exist today there. But this inference, I think there could definitely be a cost benefit trade-off that totally works, where you could 80% utilize or 50% or 60% utilize those chips, because you're just, you're going from your million chips to like 1.2 million chips. And so like, it's not that much additional expense for you to get those, 0.2 million, 200,000 extra chips made. So I don't know, like this kind of gets out into the far future, and it is somewhat sci-fi and somewhat far-fetched and hypothetical at this point in time, but it is one of the things that I think we are going to be moving more towards, and especially over that time, like 2028, 2029, 2030 in AI terms is like an infinity away almost.
Yeah. So will those chips, sorry, Jordan, I'll throw it to you here in a second. So will those chips, does Moore's law apply to AI chips as well? Or we don't know?
Moore's law looks silly next to how fast these AI chips are evolving, because
really,
yes, Moore's law has almost died for CPUs, that it's hard to get CPUs to run any faster, more efficient. Like we're
hitting the limits of physics.
Yeah, they're getting better, but it's not as fast as it used to be. The thing about what we're doing now is, and the reason why CPUs are so hard is because there's a limit to how many parallel tracks that you can run with a CPU, and it's not that many. And that is the fundamental shift of GPUs versus CPUs, and then tensor cores and all this other stuff, is that they are way more parallel units of processing power. And so if you've got problems where you can do, 1,000,000 steps all side by side, because the next step after it isn't dependent on the result of any one of those things, then you can process a lot more data a lot more quickly. And that's what a GPU does, is, it doesn't matter, one pixel on your desktop doesn't care what the color of the pixel over one from it is. And so you can compute what is the color value of every single pixel independently of one another. And that was the fundamental problem that Jensen decided to tackle, because he wanted to explore this world of parallel computing, and graphics was just like the first use case. But he fundamentally believed that parallel computing was going to be the future of computing a long time ago. And he chose graphics, and that's why these are called graphics processing units, but really they're just parallel processing units. And yeah, he chose that, like I said, because it was the great place to start building this parallel computing thing. But he's always believed that there were going to be a lot of other realms, fields, whether it's science, whether it's technology, that we're going to massively benefit from this parallelized computation instead of serialized computation. And that's why they've always invested in having these libraries that help with various verticals in science, because he was looking for, what after graphics, what are going to be the next things where we can use these parallel processing units to unleash human potential. And so first it was graphics. Then the next thing really that hit big was mining for Bitcoin. And then that kind of went away as more specialized chips came in to do that thing. And then the thing after that has obviously been AI. And there are so many different, just like we've talked about, things that end up being the bottleneck for doing this parallelized computation at any one point in time, whether it's the networking, the memory, how many processors can you put in a single place? There's just a whole bunch of different dimensions. And if you make Moore's law speed process on every single one of those dimensions, then they add up to be this thing that is so much faster than Moore's law overall. And that is what we have seen from NVIDIA, that they're, doing more computation per watt at a rate that is way in excess. If Moore's law might give you a doubling in a year and a half, in AI, you might get 100 times in a year and a half. And it's because we are, like I said, doing this parallel computing, and we're figuring out how do we solve the memory problems? How do we solve the networking problems? How do we solve the processing problems? How do we solve the software problems to do all of that? And like every single one of these things, they all multiply together to give us that total speed improvement.
And so the takeaway here is that each unit chip of compute of either inference or training over time, very, very quickly for the next 5 to 10 years, is going to get way, 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 way smaller. And it's going to get way, 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 way better at calculations. And it's going to use way, 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 way less energy. Is that fair?
Exactly.
And they're going to integrate more on each board or set of chips. And that's important because you're going to be, for instance, the Colossus 2 data center that XAI is working on is going to have 1 million GPUs. The more that you can put on each one of these boards, the less networking it requires, the faster that these data centers can come together, and the more efficiently the whole thing will run. So it's economies of scale, basically. So and that's why these like GB200 GPUs, they use, if you include the overheads, it's something like 2 to 3 kilowatts per GPU. So they might just keep getting bigger. Who knows? But yeah, the more that they can, the larger they can make each GPU, the easier it is to build the data center, because each component of that data center is larger. So instead of like 100 GPUs, you might need 10 or 50 GPUs. So that's a lot less cabling.
Got it.
And more efficient resource-wise, because between every one of these GPUs, you need miles and miles of cable, or hundreds of miles of cable between all these GPUs. So that's a lot of copper.
The end result becomes a lot easier to achieve because of all these efficiency gains.